and in relative structure drawings, you should have at least a pretty tight connection with. So that when you see a reaction, you can be like, that's an elimination. Okay? That will help you decide what reagents you need to use. Okay? So it can help you cut back on what you need to memorize, or the specifics of what you need to memorize. Okay? Which is then going to set us up with the next sequence. We're going to do that little activity again. So you can get up and find your group. I think we're ace through 5. There is a joker floating out there. The joker can do whatever they want. Diamond's going to be the writer. Heart and spade are going to support. Okay? The writer is the only one that can write. Okay? The 2 of clubs is also a writer. I will read the names of 2 compounds. The writer will write. And then the group will determine anything they can to associate to those 2 compounds. Wow. Really broad. Let's see what we can come up with. So, find your groups. Find a board. Find a pen. Fun. It is absolutely fun to play with the concepts and move them around. What you are saying is not fun is getting graded for that. Okay? That I completely agree with you, and there isn't a whole lot I can do about that. But if we can remember to keep kind of that fun behind what are we seeing in these structures, what are those connections, that can help keeping you coming back to the material, keep playing with it, working with it, and improve the odds that at the end of the semester you get the grade that you want. Right? Because if you think only about the grade, you're going to lose the breadth of material that you're trying to process, and it's just going to become unbearable. So where was I going with this? Right? So 2 places. I'm going to cheat. Right? I was going 2 places. 1, a little bit of nomenclature practice, because might as well. I mean, everybody seems to know nomenclature better than everything else, so I figured everybody would be okay with that. Okay? Because none of you are me, which is a very good thing. Okay? We've got our cyclopentane. We have the 1-bromo. So let's clear some of that out of there. And we have the 2-methyl. Why does the bromo get the 1?
Because it has the B and you take the alphabets first.
Halogens versus alkanes have no difference in priority. So to differentiate that numerical, we have to go alphabetical. Why? Some old white dude said so. Okay? It is that arbitrary and stupid. Okay? The next part of it, we had the trans 2-methyl cyclopentane 1-ol. I intentionally threw the 1 in there. That's officially IUPAC. Nobody likes seeing the 1 in there. It disrupts the end of the name and they freak out. Typically, where do you see the 1?
In the front.
Where in the front? There's a lot of front. In front of the N?
No.
Be more specific. Because yes, I agree with
Before
you.
the methyl.
If we put it before the methyl, so trans 21 methyl?
I meant after the methyl.
Are you just guessing now to mess with me? You're right. It typically drops in after the methyl. We could have said 2, 1, but then that starts to suggest there's 2 methyls. It doesn't say dimethyl, it's 1 methyl. So the 2 refers to the thing immediately after it. By dropping the 1 in front there of the cyclo, what is it then referencing? Well, it can't reference the cyclopentane because that's not a functional group. The only functional group it would be referencing is the ending, which would be the ol. That's our alcohol functional group. So there's our alcohol. Sorry, I want to make some adjustments to make this a little bit easier to track, maybe. Our alcohol, and then our methyl. Extra piece of information was thrown in this. Trans, officially, not appropriate for the name of a compound. Trans should not be used for this. What should be used is E and Z only applies to alkenes. This isn't an alkene. This has to imply R and S. The trans, cis-trans monikers can get associated with rings that only have 2 primary groups. We only have 2 primary groups, So as a hand-wavy gesture to not having to dissociate R and S with this, we could drop in the trans behind this. Okay? I considered, very briefly, being like 1R, 2S, 2-methylcyclopent, 1-ol, and I thought that was just too much of a knife in the back. Right? So I figured the trans was a decent enough shortcut on that we could at least get there. Okay, which is great. Everybody got that. Right? We start to notice pieces of nomenclature coming back, functional groups, relationships between groups. I had a bunch of people write down stereocenters. Fantastic. Those are stereocenters. So are those. Why did we not specify wedges and dashes for those?
You've got a racemic mixture or some mixture thereof.
We've decided it wasn't relevant to the question, so we removed that information. It could mean that it was a racemic mixture, just a blend. Typically, it just means it's not relevant to what we're trying to get at. Okay? The next part, people started to say, oh, well, maybe these things could react. And they started to say, whoa, well, we could go this direction. Well, what are the differences between those two pieces? Okay? And maybe it was accidental and people just started writing up stuff. Okay? But I would bet it was internalized. You noticed that there was a difference between these two structures. What is that difference? Yes, the wedges and dashes. You kind of zeroed that out. That's okay. I don't blame you.
You've got different functional groups.
Bromine versus OH. So if I'm going to make that transition, what do I want?
Substitution.
I'm going to need some source of OH to do a substitution reaction. Okay? Should that OH be negative?
It has to be positive. Because the bromo will come out
Okay.
negative.
The bromine's going to come off negative, leaving the carbon
Oh, yeah.
positive. For the oxygen to bond to the carbon, what needs to happen? The oxygen would need to supply electrons. Does it have to be a negative supply of electrons, or could it just be a lone pair? What would change?
Hangman?
Yeah, well, that's not what changed. Does it help if I not stand right there? No, that's awesome. You put a guess out there. Everybody else was silent. You did more than anybody else did.
E.
Shh. You're not allowed to judge. What's that?
Weak.
Oh.
Give us one more word that would be easier.
It's one word.
I mean, one more letter.
What change? What would change if we switch that OH from being negative to just being a normal neutral OH?
Better.
It would,
No.
You can't have a negative normal rate.
You can have an OH with a lone pair of electrons that is not negative.
Then it's a radical.
We're gonna die.
This is cool. This is cool. We're having a discussion about these structures and trying to think through it. And one of the things that I'm noticing, which is fantastic, you are all fantastic and phenomenal thinkers. Unfortunately, when you're stuck in your head, you're going to go through endless loops reiterating the exact same mistakes. Instead of keeping it in your head, what should you do? Write it down. I said we could get an oxygen with a lone pair of electrons that was neutral. Water,
Yeah.
that only makes up like 80% of our existence.
It's connected to something else, but
Okay. So, what would change if I switch between water versus OH minus?
reactivity.
I could have. No, I didn't.
Oh.
It's very possible. Okay, it's the mechanism.
You gave us one M, not two.
Oh.
That changes things a little bit.
Oh.
I don't know.
You're recording this. You can't.
The mechanism would change. If we had hydroxide as a negative, what mechanism is that going to initiate? SN2. We have a strong nucleophile. Strong nucleophiles push SN2, which would mean we get backside attack. Where's the backside of that carbon-bromine bond? Wedged or dashed?
It doesn't matter.
Look at your answer. Damn well better matter because we specifically showed that as wedged.
So it can't matter.
That starting material, we said we haven't specified wedges and dashes, which means the end result of using hydroxide, it could be wedged or dashed, in which case, hydroxide, wrong. Doesn't complete the reaction as shown. So that must mean it's water, for those of you that jumped out and tried water. That pushes an SN1 mechanism, which means the oxygen attacks a carbocation. And the carbocation has p orbitals, or a p orbital with electron space for electron density, either wedged or dashed, which means
Doesn't work.
also doesn't work, you sneaky little mother. So what do we have to do?
Reverse the arrow.
We could try and reverse the arrow. Okay? That is a distinct possibility. But even if we reverse the arrow, that may say that bromine could be either direction. But is the methyl going to be either direction? No. The methyl is locked into one position. Where this focus was going was indeed left to right. So a couple people were like, there's a reagent that does this thing. I don't know what it is. That's fine. Walk through the reagents you have and be like, crap, those didn't work. Now you can at least acknowledge that that path didn't work. But if it wasn't written down, you don't have that information. It's almost always written with THF, which I find irritating because it's just the solvent, followed by I agree with the H. It's only half right, though. And the NaOH is also there. H2O2. H2O2 and NaOH. That is our borane reagent. Borane reagents do what kind of chemistry? Addition. To do an addition, what do we need to have? Too vague. You'll always need lone pair electrons. What we're going back to is those reaction classes. In an addition reaction, what do you need to add to? A pi bond. You need an alkene. Do we have an alkene? No. That's that first arrow. I need to do an elimination reaction to start to get an alkene so that I can do an addition that gets me the proper stereochemistry of the final product. How do I run that elimination reaction? What do we need for an elimination? You all reviewed that slide where I summarized those reactions and were like, these are the pieces. We need to break 2 sigma bonds. Yes, which sigma bond are we going to break?
The bromine.
The bromine. Fantastic. What's our other sigma bond?
Hydrogen.
Hydrogen. Is a carbon-hydrogen bond easy to break?
Not terribly, no.
Not really. The carbon-bromine bond is actually pretty decent to break because
Electronegativity.
there's a large difference in electronegativity. Carbon to hydrogen has a very small difference in electronegativity, which makes that bond rather difficult to break. So how can I get it to break?
Heat.
I can add a bunch of heat to this, represented with the delta. I could also add something else. More boron? No, base. Add a base to remove the hydrogen. That hydrogen needs to come off as H+. Why do I know that hydrogen needs to come off as H+? What's the bromine going to come off as? Br-, leaving a partial positive carbon there. To make the pi bond, what do I need?
Electrons.
Electrons, which means
You have to take them.
this carbon would need to be
Partial negative.
partially negative. The only way it becomes negative is if the hydrogen leaves as H+. Okay? All of these pieces stack and follow through. Do you have to know each of those pieces to figure out the answer? No. What would you have to know?
The reaction.
Reagents.
All of the reagents. How many of you knew the reagents? How many of you knew all the individual pieces?
Everyone.
Welcome to day 2. Okay? You need to be thinking about both of those sections. Some of it is raw, do I know the reagents that allow me to do it? The other part of it is how can I transition between these structures? Okay? And if you feel like crying, that's good. You're acknowledging it's a challenge. Okay? It will be a challenge. Okay? But now you know what you need to target. You either have to memorize the crap out of reagents or memorize the crap about how all of these things work. Both of those as individual methods have problems. You really need an overlap, a blend of both. Okay? Questions? Don't you love like when people shine a flashing light at how much of an idiot you are? Like it's awesome.
It's pretty great.
Okay? Yeah, I love it all the time. Okay? It happens way more than I care to admit. Okay? But that's what we're working towards. Okay, so back to our labels. We talked about the labels, the difference between acids, bases, and electrophiles and nucleophiles. Our acid-base definitions, Mustafa brought in the Arrhenius. Throw it out the window. I don't even want to hear about the Arrhenius definition. We then have Bronsted-Lowry, and then we have Lewis. Lewis is way too broad. Ignore Lewis. So when we talk about an acid and a base, I'm specifically referencing only Bronsted-Lowry. Okay? That is a huge shift from your backgrounds. I think at least 3 of you had chemistry or OChem at Mesa. I know for sure that Professor Minger references acids and bases as Lewis acids and bases, not as Bronsted-Lowry. I think that's a massive confusion because everything is a Lewis acid and base. Okay? When I reference acids and bases, Bronsted-Lowry only. We're looking at the transfer of protons. Okay? If it does something other than the transfer of a proton, electrophile, nucleophile. Okay? Those are our primary categories. When you look at a species, those are the labels you should be attaching to them. Okay? Acid-base review. Okay? I forgot how I was going to sequence this. It didn't work so well, so we'll try it again. Name an acid.
Hydrochloric acid.
Hydrochloric acid. How about another one? HBr. HI.
Acetic acid.
Acetic acid. HF. Did anybody consider that molecule, acetone, as an acid?
Yeah,
Yeah, I did. Not really. You're really good at hedging that. I like it. Okay? That is an acid. Anybody see the hydrogen?
Oh, yeah, there's 6 of them.
There's 6 of them. Welcome to day 2 of OChem 2. Okay? Hydrogens get implied. And those acidic hydrogens become incredibly important. For those of you that have moved through biochemistry, what we're about to show is the fundamental reason why biochemistry exists. Right here. That hydrogen is about as acidic as the hydrogen on water. Okay, so if we were considering like HCl, HBr, HOH. Which of those is the strongest acid? HBr. Why?
Because the size of that means
It's the biggest. Remember I said the reactivity of things? Charge. We all establish the same charge on all of those when they lose the hydrogen. The next most important thing is size. Bromine's the biggest. That makes it the most stable, which means HBr is the strongest acid. Okay? Water. Totally not acidic, right? It's totally not acidic because oxygen's not electronegative enough. This hydrogen right here is connected to what? Carbon. That hydrogen has the same acidity as water. Does carbon have the same electronegativity as oxygen? Then why the hell does that have the same acidity as water?
Because of the oxygen on the top.
Because the oxygen on the top, what does that have to do with it? Okay. If we go through and draw out the results of removing that electron or that hydrogen, we would have a negative charge here. Negative carbon, horrible, not stable. We would say that's not going to happen. But lone pair electrons allowing me to do resonance, I can put that negative charge on an oxygen. Is a negative oxygen roughly the same stability as a negative oxygen?
Yes.
Yes. Why is that hydrogen acidic? Because a resonance contributor puts the negative charge on an oxygen. Was that resonance contributor obvious? Should have been, yeah. Everything in OChem 2 is it should have been obvious. I should have gotten that right. That comes with practice, being able to build at these. How many of you enjoyed resonance in OChem 1? All of OChem 2 is resonance. Okay? It gets such an underplay in OChem 1. Everything we do is resonance. It's how do those electrons move? If we don't evaluate it at that level, what do? You memorize. So when everybody goes, so OChem was the worst class ever, I had to memorize so much. It's because your instructor didn't talk about how to actually move things. Or you missed that aspect. Okay? There's no more memorization in OChem than any other class. Okay? So, acid. We can remove that hydrogen. It's a proton donor. Cool. There we go. Okay? Let's try that compound. What do you think? Could that one be an acid?
Yes.
Trick question. No, it can't. Yeah, it can. It's actually more acidic. Why is it more acidic?
Because you've got more resonance forms. There were two on the first one.
Why is that hydrogen more acidic than this one? Because I'm hearing more resonance. You should play around with that. You're going to have a hard time showing me that more resonance.
Because it's bigger.
Nice try. No. The reason why the red hydrogen is more acidic than the orange hydrogen is because of an inductive effect. There's another oxygen out here that can withdraw electrons through the structure. That red hydrogen is not the acidic hydrogen. Where's the acidic hydrogen? In the middle, because
It's got the least
More inductive
electron
effect.
density around the carbon.
where could that negative charge resonate?
Either way, two different oxygens.
It could go out that way, or it could go out that way. So those of you who were saying more resonance, that is absolutely why that structure is more acidic, but not referencing that hydrogen. Okay? So we have to remember these layers that go with it. In OChem 1, there was one answer. This is the acidic hydrogen. OChem 2, there are 6 hydrogens. You have to decide which one's the most acidic. How do you know which one's the most acidic?
Resonance.
Charge. Size, electronegativity, resonance, and induction. You have to apply those rules to each of those structures, or you hope that you can memorize every possible structure that could show up on an exam. When people say there's a lot of memorization, that's what they tried to do. Okay? What about this one? So we said this one was more, this one was less. What about this one? Should it be less squared or more squared?
It's in the middle.
Did you just say that just because I only gave you the caps? And you're like, I bet you he's being a jerk? Yeah, it's in the middle. Why is it in the middle? Because, dude, you drew it in the middle.
No.
What do you got?
There's both resonance and an inductive effect.
Both resonance and an inductive effect, which would make it... Actually, I processed this wrong. Sorry.
Wouldn't that make it stronger? If it has
That should make it stronger, right? Okay. Turns out when we look at this one, that's so not the word I should have used.
Least.
Yep, there we go. It's the least electronegative. But if it had resonance and induction, doesn't that make it more acidic? Yeah, it would. Before we get to induction, what do we encounter? Charge.
Size. Electronegativity.
Resonance. Ding, ding, ding. That red arrow does resonance, which does what to that carbon?
Exceeds the octet.
Makes it less positive. If it is less positive, how easy is it for those electrons to go that way? It becomes less likely. There's a counteracting resonance in this structure that makes it less acidic. What? Yes. Okay. Layers. Which one's the stronger base? Sodium hydroxide or acetone?
sodium hydroxide.
Okay, why? You said acetone was an acid. Can acetone be a base?
I guess so,
Yes.
yes.
How?
It has lone pairs on the oxygen that come down into
To be a base, what does it need to do? Have electrons to donate. Does it have electrons to donate?
Yes.
Yeah, it technically has two. It has a lone pair and a pi bond that it could potentially pull from that could go to an H+. That does make acetone also basic. Why is sodium hydroxide a stronger base than acetone?
Because
ionic charge.
the difference.
It's an ionic bond making the oxygen
OH negative.
negative, which is a stronger base. A negative oxygen or a neutral oxygen? Well, the first thing we should check would be charge. Negative is stronger than neutral. Okay? And ultimately, better to reference it as a partial negative because there's a resonance contributor making the oxygen negative. Okay? Which is a stronger base now? Sodium hydroxide or potassium hydroxide?
Let's see.
Potassium.
Potassium.
Why is potassium the stronger base?
Because the halogens is the opposite way, and then with the number alkaline metals is the opposite way. So
I'm not going to say you're wrong, but I have no idea what you're talking about.
So,
It's the size.
So with that one, well, I just remember the rules. This is memorization.
Yeah, and that's fine. There are ways to memorize it. And full disclosure, I am horrible at memorization. So if you've got some weird, cute mnemonic device that helps you memorize things, share it with the class. Gloss. Complete gloss over. I'm going to have no idea what you're talking about. But
so with
share
the
away.
halogens, fluorine is the most reactive. Going down, it decreases.
With what?
Well, what do you mean? Like, why
And
does
even
it decrease?
that, it becomes more acidic.
Yeah. No,
as
it
you go
becomes
down.
less acidic. Or-
HI is a stronger acid than HF.
Well, let's talk about the actual.
Do your bases thing? Okay.
Yeah, and then the other way around is lithium hydroxide would be the strongest acid. So I guess I messed up, but I mean it flip flops. That makes sense.
So this is the danger with memorization devices. You ultimately got the answer right. All of the science behind what you just explained was horribly wrong. Okay, and that's why I have problems with those.
NaOH, the stronger one.
It is potassium hydroxide.
Oh, okay. I thought the smaller.
Potassium is larger. What does that have to do with it?
That's with
I thought
the,
it
more
was
stable,
larger,
but-
it was more acidic.
Are we asking about acids?
So the smaller one would.
Charge density.
Okay, what is that charge doing? Why does it matter that potassium is larger? When we talked about size, we were talking about the size of the conjugate base. Sodium and potassium aren't the bases here. The hydroxide is the base. That's where the base characteristic is. And in that case, the size is not different. It's oxygen versus oxygen. So why is potassium hydroxide a stronger base than sodium hydroxide?
It dissociates.
Difference in electronegativity.
It dissociates easier. Why?
Because it's got a bigger charge.
Because potassium is bigger, which means the overlap of orbitals between the potassium and the hydroxide is weaker, which means the hydroxide is now more available to react. Okay. Next one. Stronger or weaker?
stronger,
Why?
some memorization again.
Okay. It helps if we make them equivalent, so let's make sure they're both negative. Why would the amide be a stronger base than the hydroxide? Where do we start? Charge.
Same charge.
So irrelevant. We move to size. Nitrogen versus oxygen.
Electronegativity.
Okay. This is where we're going to run into a smattering of answers. Those people that had me are like, there's no difference in size, it's irrelevant. Everybody's like, what the hell are you talking about? There's clearly a difference in size. I memorized that trend in Gen Chem. You're absolutely right. It's also irrelevant. Across a row, the size change is so small, it is negligible. It has very little contribution to the overall reactivity. Because nitrogen and oxygen are in the same row, there is no size difference, which means charge and size don't count. We then move to electronegativity. How does that have an effect?
Nitrogen is less electronegative.
Nitrogen is less electronegative. Well, shouldn't that make the oxygen more reactive if it's more electronegative?
No.
No, it holds the electron.
It's holding the electrons. And you had a really good point. You said, well, the electronegativity back in acids, the more electronegative, it became more acidic. Why is it changing? What are we looking at? We're looking at a base instead of an acid. Acids and bases are opposites, which means the rules of how we memorize those flip. You have to know the rule behind it, not just a raw memorization, because the raw memorization can get you into trouble. When we talk about those 5 things, I'm not saying charge is always better. Okay? Charge just makes it more reactive. Okay? Size, bigger isn't necessarily better. Okay? Depending on what I'm looking at, be it an acid or a base, the interpretation of that size is going to change. Those 5 things that I want you to understand and hold to, in that order, by the way, you have to overlay on top of the definitions. Do you not have the definitions memorized? Well, then you get to memorize all the reagents. Okay? The definitions can allow you to group the reagents now. You don't have to memorize every single reagent. You just have to know how to manipulate them. Okay?
So why is it stronger?
The nitrogen is less electronegative. What does a base need to do? Donate electrons. Because it is less electronegative, which one's more willing to share those electrons? Okay? Sodium hydride.
Weaker.
No, that's just strong.
Charge. Same. Size.
smaller.
Hydrogen is the smallest element. Okay?
So
We're concentrating that charge into one spot, which means sodium hydride becomes the strongest base. I'm trying to close you, you stupid monkey, not continue the slides. Okay? So sodium hydride is the strongest base we have access to.
So you're
Well-
talking about size in terms of shells?
Size of the atom size, it ties effectively back to shells, but we don't have to get that nuanced behind it. Okay? Why does all this become important? Well, if I want to run this reaction, acetone to this negatively charged species, which base do I use? Just to make you feel bad, there is multiple wrong answers.
NaH.
NaH is one of the wrong answers.
All right, then it'll be NaOH.
Why'd you do that?
Because if it's not the strongest, it's the weakest.
And you might be, well, that's a BS. No, that's a pretty solid explanation. Pick your extremes and then kind of weed out in between. Why does that one work? Well, what would the result have been if it was NaH? So this was NaOH. If I had done NaH, what would I have gotten? Because we are kind of out of time. They're the same, dude.
No.
Are they?
One is a unidirectional, one is going back and forth. Equilibrium.
Sodium hydride is such a strong base, it removes the hydrogen and it makes that reaction irreversible. Sodium hydroxide is not a strong enough base. It only removes some of the hydrogen, leaving me a mix of both of those species. You're like, well, that's not a big deal. When you go through to mix a reaction, I want to mix A with B to get product C. Okay? Is it going to change the reaction if I mix A, B, and D? Yeah? There's another species there that can do things. In the case of the equilibrium one, there's another species floating around. In the case of the unidirectional one, there is no other species. Okay? Like, we didn't learn about that in 235. That's because this is 236. Now, legitimate second semester material. Equilibrium comes in with a vengeance. Okay? And we have to be aware of what materials we're using to run reactions, because if we use one material, it leaves some species around that could do something else. If we use another material, it gets rid of everything. Okay? This brings in the concept of kinetics and thermodynamics and equilibrium. You're like, God, those were all terms that I associate with Chem 152. Yes. That's what OChem is. OChem 2 is taking Gen Chem 2 and OChem 1 and smashing them together in some glorious monster. Okay? And with that, with like 2 slides advancing through the show,